the indeterminate form of type 0 over 0. Sometimes when we are evaluating the limits of irrational functions by using the direct substitution, we get the limits of the top and bottom functions are both 0. In this case, we say that the limit has the indeterminate form 0 over 0. In this video, you will see the main techniques for evaluating the limits of functions for which direct substitution fails. By the way, if you liked this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. Suppose we were asked to find the following limit. If we apply the property of the quotient and substitute minus 3 for x, we get 0 over 0, which is meaningless as a real number. Therefore, the direct substitution failed. This outcome is called an indeterminate form because we don't know whether or not this limit exists or what it is if it exists. A rational function is a ratio or fraction of two polynomials. When both the numerator f of x and the denominator g of x of a rational function approaches 0, as x approaches some point a, the limit of a rational function is said to be of the indeterminate form of type 0 over 0. You will now see the main techniques for evaluating the limits of functions for which direct substitution fails. Evaluating a limit by factoring and cancelling. Let's begin with the previous example. If we substitute minus 3 into the function, we get 0 over 0. So direct substitution will not yield the limit. The limit may or may not exist. So we have to do some algebraic manipulation to get rid of that form. The numerator is a difference of squares that can be easily factored. Factoring first and simplifying, we find the limit. It's important you realize that the graph of the original function would be the same as the graph of the linear function y equals x minus 3, with the single point minus 3 and minus 6 removed from the graph. Let's see another example. You should always try direct substitution first. Begin by substituting 1 for x into the function. Because both the numerator and denominator are 0, the direct substitution yields an indeterminate form 0 over 0. So begin by factoring the numerator and denominator. The numerator is a quadratic form, and we can factor the denominator by grouping. I will show you how to factor these algebraic expressions step by step. Pay attention. After factoring in both the numerator and denominator, you cancel out the common factor. Then try direct substitution again. The limit as x approaches 1 is 4.5. The graph of the original function would be the same as the graph of the new rational function, with the single point 1 and 4.5 removed from the graph. Let's see another example. You should always try direct substitution first. Begin by substituting 4 for x into the function. We can see that the direct substitution fails again. So begin by factoring the numerator and denominator. I will show you how to factor these algebraic expressions step by step. Pay attention. After factoring in both the numerator and denominator, you cancel out the common factor. Then try direct substitution again to evaluate the simpler limit. However, substituting 4 for x yields 9 over 0, which is meaningless because infinity is not a real number. Hence, this limit does not exist. Look at the graph. When the limit exists, it must be unique. So we can see that this limit does not exist. Evaluating a limit by rationalizing technique. Rationalization means to multiply the numerator and denominator of a rational function by the conjugate of the numerator or denominator in order to eliminate radical symbols. We try this method for rational functions that contain square roots. Let's try this one. Evaluate the limit. Remember, you should always try direct substitution first. By direct substitution, we obtain the indeterminate form 0 over 0. In this case, we rewrite the fraction by rationalizing the denominator. We multiply the numerator and denominator by the conjugate of the denominator. In fact, we multiply out the denominator. We don't multiply out the numerator because we are hoping that the x minus 2 in the numerator cancels out in the end. After cancelling out x minus 2 from the numerator and denominator, we evaluate the simpler limit. Let's evaluate this limit. By direct substitution, we obtain the indeterminate form 0 over 0. So we multiply the numerator and denominator by the conjugate of the numerator. We multiply out the numerator. We don't multiply out the denominator because we are hoping that the x minus 9 in the denominator cancels out in the end. After cancelling out x minus 9 from the numerator and denominator, we evaluate the simpler limit. Evaluating a limit by simplifying a complex fraction. When factoring and conjugate multiplication don't work, use a different strategy. Try other basic algebra like adding or subtracting fractions, multiplying or dividing fractions, cancelling, or some other form of simplification. Let's see how it works. Evaluate the following limit. Begin by substituting 1 for x into the function. You will see that the direct substitution fails. If we look at the fractions, there are no square roots or algebraic expressions to factor. The algebra skills necessary to solve this limit involve division of fractions. The rule is summarized as follows. We now apply this rule to our problem. We simplify the numerator and multiply by the reciprocal of the denominator. It's important to note that 1 minus x and x minus 1 are opposites that cancel, leaving minus 1. Do not multiply the denominator because we want to be able to cancel the factor x minus 1. We now evaluate the simpler limit. Let's see another example. Both fractions fail to have a limit when x approaches 2. The direct substitution does not work here. If we look at the fractions, there are no square roots or algebraic expressions to factor, as in the previous example. The algebra skills necessary to solve this limit involve subtraction of fractions. The rule is summarized as follows. Since neither of the two functions has a limit when x approaches 2, we cannot apply the property of difference for limits. In this case, we find the limit by performing subtraction. So we factor the denominators and then we combine the fractions by subtracting the algebraic fractions. After cancelling the factor x minus 2, the direct substitution rule is applicable and we evaluate the simpler limit. First, due to the zero produced in either one of the denominators, the direct substitution fails. Since neither of the two functions has a limit when x approaches 0, we cannot apply the property of difference for limits. In this case, we find the limit by performing difference of fractions first. Next, we must get rid of the roots. So we rewrite the fraction by rationalizing the numerator. We multiply the numerator and denominator by the conjugate of the numerator. It's a hard work. Pay attention. After cancelling the factor x, the direct substitution works and we evaluate the limit.